Factorials and permutations. Also discovering the two buttons on your calculator that you've never used before. An exclamation mark for the factorial, and permutations is the NPR button that's there. There's no way to say it other than factorials and permutations are lazy ways of doing calculations. There is no new math here, it's just multiplication and patterns. But mathematicians don't want to go and write out something like 12 times 11 times 10 times 9 times 8 all the way down to 1, where they could just do 12 factorial. This is going to look complex. It's going to look like a language, but even when you get into it here, there's really nothing different happening than your basic BEDMAS operations dealing with brackets, your division, multiplication. And when you see this exclamation mark, which is a factorial, that means just multiplying in a pattern that goes down. And so when you see a 6 factorial, that just means 6 times 5 times 4 times 3 times 2 times 1. 8 factorial over 5 factorial is a fraction of 8 times 7 times 6 all the way down to 1, and then divided by 5 times 4 times 3 times 2 times 1. And what that means is that there's going to be a lot that cancels out. So all this is a shortcut, and when we get into real life problems, you'll realize that this isn't just some kind of math for math's sake. This actually represents 8 people that you could line up, or 8 different people that you could pick for an event, and how many different ways could you arrange them. Or if you had 6 pictures on a wall, how many different ways could that be done? Or something more complex, a 12-digit password where you can't repeat numbers. You've got 12 options for the first digit in the password, and then continuing down from there. So that's what we'll do with accounting, but we're going to start off by just getting some basic definitions in. So first, a factorial is an expression that involves the product of a series of consecutive examples. This here we do not call 5 exclamation. It's not like a really excited 5. It just means 5 factorial. And that is a way of saying 5 times 4 times 3 times 2 times 1. And if you put that if you wrote that out, you would get 120 in your calculator. But ideally, most of you will just be pressing the 5 button on your calculator, and then pressing the exclamation mark, the factorial button, and then from there you should get 120. So take a minute, get out your calculators, and just figure out how to use that factorial button. And even something like this you should be able to do. 8 factorial, hit the divide button, and then 5 factorial. And then something like this you will not be able to do, because for the most part your calculators can't handle anything above 50 factorial. So I'm purposely going to give you questions like this to see if you could actually understand how the patterns work, rather than just using technology. What's our general form? N factorial. It does not matter what number's here. If this is a 10, it's going to be 10 factorial. If it's a 12, it'll be that, and it'll continue down. So if it's an n factorial, I have to start with n, and then I'm going to multiply it by the next number. And the next consecutive number is n minus 1. And now the next one will be n minus 2. And if the algebra frustrates you, just pick a number in your mind. This is 15. Now 15 minus 1 is 14. 15 minus 2 is 13, and I'll continue down. And if you get this pattern, it'll just continue. But it doesn't matter whether you start with a 5, a 20, or 100 factorial. By the time you get to the very end, you're going to have 3 times 2 times 1, because every single factorial decreases this way. That's a general term. Factors are also an iteration, and an iteration is just a pattern that has some level of change. In this case, our factorial is an iteration where you are multiplying by 1 less each time. So with 6 factorial, I'm starting with my 6, and then I'm multiplying times 5, times 4, times 3, times 2, times 1, or you'll go to your technology. If I know 5 factorial is 120, and I multiply that by 6, I'm going to be getting 720 as that answer. And it's fine if you're using technology on these. I'm going to leave a couple of the ones that are a little bit simpler for you to work through. I mean, anything divided by itself, hopefully you should be able to get that. On EdSpeed, there will be an answer key for all of this. I want to look at some of the ones that are a bit more complex. The other thing is that when we're multiplying, sometimes the x's get a bit confusing. Traditionally, mathematicians will use a dot to show the multiplying, primarily because it is faster, but also because it doesn't get confused with this being an algebra x. So this is another fine way to see it, and I'll do that for most of the other ones. 97 divided by 94 factorial, there's no way that I'm going to write all this out, and I don't need to, because I know that 97 factorial is 97 times 96 times 95 times 94 times 93. But why have I paused here? This is the number I need to deal with. This is a true statement. 97 factorial is 97 times 96 times 95 times 94 factorial. But I want to purposely stop there because in the denominator I have 94 factorial. And when it comes to the BEDMAS rules, where I'm doing multiplication and division in the order they come, there's nothing that stops me from doing the division portion here. So now the actual answer is 97 times 96 times 95. And then from there, you can put it into your calculator. And that's the case with most of these. Here, do the BEDMAS first. 9 minus 3 gets 6 factorial over 5 factorial. One like this, you need to go to a calculator, and there's no way you're going to write the entire number out. So this is a situation where you're going to have the decimal, and you're going to do the scientific notation that you would have done in an earlier science class, where you do times 10 to the exponent. Different calculators work in different ways. Some are going to give you a decimal, and then it's going to say an E, and then there'll be a number like 12. That's saying that your exponent is 12. Other ones will show it using the proper times 10, and then putting the exponent in from there. So take time to work through and just try some of these questions. The key is to make sure technology is working, and then we'll look at some of the more complex algebra ones. Remember that a factorial just decreases. And so if I'm starting with n plus 1 factorial, all I need to do is have that decrease with the goal of being able to cancel out what I can here. So in this case, I'm going to leave the n factorial in the numerator, but this n minus 1 factorial, I want to become an n minus 2 factorial so that I can cancel it out. And I can do that, because n minus 1 factorial is just n minus 1 times n minus 2 factorial. And so, just so you have it visually, this piece becomes that piece. What about in the denominator? My n plus 1 factorial I can start by writing out, and then I can do n, which is 1 less, factorial, giving the same number that I have in the numerator. This n minus 2 factorial, I'm just going to leave here. Now we do the canceling. This is gone, this is gone, this is gone, this is gone, and I'm left with n minus 1 over n plus 1, and that's the simplest form. There's nothing I can factor, there's no other way to reduce that. The reality is that this question is only for those going for a goal of 90% or up. This will be a true-false question on a test. It'll be one question on the choice section. So you need to be able to do things like this for the theoretical math, but for most of us, it'll just be the practical piece here, and also looking at how to actually do these as part of word problems. The questions here that involve the equations, it's the same approach as above, where you'll start with your n plus 2. So I'll have n plus 2 factorial, or n plus 2 times n plus 1, down to n factorial. These cancel out, and now I'm left with grade 10 algebra. So you have a question where you would have to do FOIL, you would have to expand it, bring the 6 back to the other side with the goal of solving for n. So all of the answers for this will be put up onto EdSpeed. At this point, we're just trying it, but remember, both these questions are just for those that are aiming for 90% and above. This can be left till next week too, because it's more important that you focus on the main patterns. Permutation. When we're dealing with a permutation, This is an arrangement of numbers, but there's nothing that says you always have to use the entire factorial. So for example, if I have 10 people and I want to arrange them in a line, 10 people in a line is going to be 10 options for the first person in line, then 9, and then all the way down to the last people that are being picked. And that is only 3 options, 2 options, 1 option. You put it into your calculator and get the actual answer. But do you always have to pick 10 people from 10 options? Absolutely not. There's nothing that says that you can't just pick 2. So you have 10 people and you want to pick 2 of them. And in permutations, we take that letter P and show this as 10 people, and I'm going to pick, or I'm going to permutate 2 options of them. So 10 total, I only want to know the permutations of 2 people. And in that case, it would be 10 times 9, means there are 90 ways I could go and pick 2 people. If I wanted to do 5, it would just be 10 times 9 times 8 times 7 times 6, because that's the 5th position and the options that we have. So let's look at this more in a general term. A permutation is an arrangement of all items in a definite order. The number of permutations of n distinct items is n factorial. But anytime we use an n, you can just pick a number like 15 and put that in. The permutation notation for this is npn. So using my 15 example, 15p15 is equal to 15 factorial. When it comes to doing work in class, it doesn't matter which one you use. I tend to be lazy and just use the 15 factorial, but 15p15 is the exact same thing. So for example, 5 people, 5 positions, n is equal to 5, 5p5 is equal to 5 factorial into your calculator, and you have 120. So that means there are 120 ways of arranging 5 people. But what if you had 5 people, but only 3 positions to fill? What does this value become? This becomes the second value in our equation. So the number of permutations of our items from n distinct items is 5p3. The formula that's here is a general term. And all this tells you is that of your total people, the denominator is going to be the total minus the number that you actually want. So note that NPR can also be written as PNR. Those that do more pure mathematics, you're actually going to see it written this way at certain universities and in certain programs. The reality is that unlike the Pythagorean theorem, which is 400 years old and everyone uses c squared is equal to a squared plus b squared, this area of math is only about 40 years old. And so different people that have developed the use of this have used different forms. I'll use this the most because it's what your calculator looks like, but different handouts you have will see this. We'll tend to avoid this because it tends to just be used kind of by the engineering calculus world when they're looking at probabilities. So example with 5 people for 3 spots on the committee, 5p3, there's the formula, reducing it, and then the 60 possibilities. The reality though is that with your calculator, you can go from here to here. You know there are 5 people, you want to pick 3 and do that. What do you do on your calculator? Hit the 5 button, hit your NPR button, hit the 3, and then hit enter, and it will give you 60. So it's worth taking time to just get your calculator figured out for the factorials and for the NPR. Are you responsible for doing questions this way? No, but you are responsible for understanding it. So a typical question that I could put on, whether it's true, false, or multiple choice, is I would say, what of the following are equivalent to 5p3? And of the solutions that were there, this would count because it gets 60, this would count, this of course would count. We could also talk about ways of using factorials for it. But if you don't like the logic of it, or if you find the theory of this frustrating, you can always use technology. So if you need to know if these 2 things are equivalent, put this into the calculator and get 60. Put 5 factorial divided by 2 factorial into the calculator and get 60. And then you know that these are equivalent. And now it just comes to calculator practice. In your calculator, hitting the 9 button, the NPR button, and the 6, and then going from there. Personally, I still like to write it out. So if I have one like this, I know this means 7p4, and that for me would be 7 times 6 times 5 times 4 factorial divided by 4 factorial, and then I go and cancel these elements out and go from there. So that's what we're looking at. Now it's just time to practice and time to go and look at word problems where we can use either NPR or factorial. So when will you use factorial? Where every single number is used. When will you use NPR? Where you only want a certain number of the total. Permutations. Factorial works great for permutations if everything is different. So if you have 6 different people lined up, the number of ways of sorting them into a line would be 6 factorial. Where it gets a little bit tricky is when you have identical items. That's not going to happen with people because people are unique, but it absolutely happens with letters. And so example, I'm going to switch this to a 7 factorial and using the last letters of my name. If I have the letters Freeman, there's 7 letters there. That means there's 7 factorial ways of representing them. But I have a problem because 2 of those letters are identical. And if I have 2 E's side by side, or if I have an E here and an E here and I switch them, I don't actually have 7 factorial ways. In fact, I have exactly half of the ways left. Because every single permutation that's there, I can go and take half of them away just for the double E's. That's the theory of it. Let's look at it in practice. If you have something like the word dole, if in doubt and you're not understanding the factorials, write them all out. There are actually 24 ways, and if you look at the patterns that are here, you can see where each of those come from. Now ideally we won't be doing that because we would say 4 factorial. And write this onto your sheet so that you can kind of go through and see the pattern that's here. This would be 4 factorial is equal to 4 times 3 times 2 times 1, giving me 24 ways. And the 4 by 6 pattern shows you those 24 options. But now I'm going to take the word dole and change it to doll, and this E now becomes an L, which means that every single time that I had an LE or an EL, I now have an LL. And the underlined portions show me all of the double counting. So I know just from looking at this that the answer is 12. But I want you to look at the pattern here. If this answer is 24 and this one is 12, how can we show this with factorials? This is the easy one, 4 factorial. Here I start with 4 factorial and I divide out by 2 factorial. Why am I dividing by 2 factorial rather than 2? Because there are 2 factorial ways of arranging these. And that becomes important on the next one where we have 3 L's and there are 3 factorial ways of arranging them. Let's just scroll down and we will look at a more practical kind of question here. And that has to do with something like the number of clothes that we have. If I have 5 pairs of blue jeans, I actually have 5 B's that are here, 2 white shirts, and then 3 black sweaters. And I'm just going to use an L for black. When I do the permutations of this, I have 5, 6, 7, 8, 9, 10 options, but I have a lot of repeats. So rather than just dividing by a 2 factorial, I need to go and divide by a 5 factorial, 2 factorial, and 3 factorial. All this goes into the calculator, and you're done.